Alrighty, so in this video I'm going to work out some example problems for work, which we learned last time. If you remember, work is force times distance, where this is a special type of multiplication called the dot product. And basically what it means is when you multiply the force and the distance, you're always multiplying the parallel components. That is, how much of the force is in the same direction as the distance. So let's take an example. Let's say we have a nice horizontal table with a block, and we have some number of forces. F1 is 100, F2 is 50, F3 is 20, and of course mg, the weight, is pulling down. And we know that F1 is at an angle of 30 degrees, like that. And the question is, calculate the total work done in moving the block 5 meters to the right. All right, so there's our question. We want to calculate the total work. So we have two ways of thinking about it. We can either calculate the work for each individual force and then add up all the works together. Or we could find the total work all at once by adding up the forces together and calculating and multiplying by the distance. Let's do the first, just for fun. Let's take the work done by F1. So the work done by the force F1. Well, first of all, I asked the question, what's the direction of motion? In this case, the direction of motion is the positive x direction. So that tells me, when I talk about the force, I only want to use the x component of the force. So I make a little right triangle with my force. Here's the x side down here. So I say the x component of that force is 100 cosine 30 times the distance, which is 5 meters to the right. The force is also pushing to the right, so this is going to be positive. So I calculate this out, and I get 433.01 joules. All right, what about the work done by F2? Well, again, the direction of motion is the positive x direction, so I only want the x component of F2. Well, the x component of F2, that's 50. The whole thing is in the x direction. How far does the block slide? 5 meters. Is this work positive or negative? Well, the distance is to the right, the force pushes to the left. They're in opposite directions, so this better be a negative work. So this is negative 250 joules. All right, work done by F3. Direction of motion, positive x direction. F3, I only want the x component of F3. However, F3 is pointing straight down. That's a y directional force. So the x component of F3 is 0. Thus, F3 does no work. Because that force, the third force, does not push and has no component of force which is in the same direction as the motion. So it's as if it's not doing anything at all. And then, of course, we could ask the same for gravity. How much work is done by gravity in this case? Well, gravity is a y-directional force. The direction is x-directional, so no amount of gravity aligns with the direction, so gravity also does no work here. Now we've got all the forces laid out, all the works calculated for each one of the forces. The total work is, of course, work 1 plus work 2 plus work 3 plus work 4. Calculate it out, and we get 183.01 joules. So the total work done in moving this box, because of all the forces acting on it, is 183 joules. Notice some of the forces caused positive work, some of the forces were negative work, so they kind of sucked up the work. And then some of the forces, even though they were applied to the box, didn't go into the work calculation at all, because they weren't in the right direction. So, let's try another example. Example 2. Let's try a inclined plane. Let's say there's a block, mass 10 kilograms, sitting at the top. Let's say this ramp is 30 degrees. And what do we know? Let's say I push on this block up the ramp with a force of 20 newtons. And I'm going to assume the block slides down the ramp, even though I'm pushing the other way. It still slides down the ramp, and it slides a distance of 5 meters. The question is, calculate the work done by A, the applied force, and B, gravity. All right, so this is going to be work just like our previous example. If you look at it, I have some number of forces acting on the box, and I calculated the work done by each of the forces separately. Now at the end, I wound up adding them together, but here, I don't care about adding them together. I just want to know the work done by each force separately. Well, let's look. What are the forces? We've got the applied force. That's one force. That's part A. And then we also have gravity. That's part B. So those are my two forces. For each of them, I have to calculate the work. Okay. Let's look at part A. The work done by my applied force. So, just like before, we say, in which direction will my block slide? In this case, my block is going to slide down the plane, down the ramp. Okay? That direction is not X and it's not Y. It's what I used to call, remember when we learned about this, parallel. It's the parallel direction. So that means for all the forces, at least for part A, the applied force, I only want to know how much of the applied force is parallel. Okay, so work is the applied force times distance. But how much is parallel? We'll look at the applied force. Is it in the parallel direction already? It is. In fact, I was told this force is up the ramp, so it's not in the X direction or anything like that, it's up the ramp. So it's already in the parallel direction. So that's easy. I say the whole force, 20. How far does the block slide? It slides 5 meters. But then we ask, is this positive or is this negative? Well, the block slides down the ramp, but my applied force is up the ramp. Since they're in opposite directions, this is negative. So, negative 100 joules. Okay, just like over here, where we're looking at, let's say, F2, the block slides in the x direction. F2 is already in the x direction, so it's the force times the distance. And then we figure out positive or negative depending on if it's the same or the opposite direction. Now what about part B? Work is force due to gravity, parallel times x. All right, direction of motion, parallel direction. The force due to gravity, is that already in the parallel direction? No, it's a y-directional force. So the first thing I have to do is take this y-directional force, which is mg, and break it up into the perpendicular side and the parallel side. And I know that is my 30-degree angle. Okay, just like before when we did inclined plane, same thing here. Here's the parallel side down here. This is the perpendicular side up here. So, with that triangle, I say, how much of gravity is parallel? Well, the parallel side is the side opposite to the angle. Opposite goes with sine. So it's m, 10, times g, 9.8, times the sine of 30. That is the force due to gravity parallel component. Times how far does my block slide? It slides 5 meters. And then I ask if this is positive or negative. Well, the block slides down the plane. Which way does gravity want me to go? Gravity is trying to slide me down the plane as well. So they're both down the plane. Since they're the same direction, then it is just positive. And I stick this in my calculator, 49 times 5, and I get 245 joules. And there we go. So here we have an example. Some system, some number of forces acting on the system, and the system slides in some direction. And I'm told, calculate the work for each one of the forces. In this case, there were 2. The applied force is 1, gravity is another. So all I have to do is first ask the question, which direction does the object slide? In this case, it slides in the parallel direction. So I take my first force and I say, what's the parallel component of that force? Here it turned out it's already parallel, so I don't have to do sine and cosine, it's just the force. Times the distance, and then I have to find out positive or negative. If the force and the distance are in the same direction, it's positive. If they're in opposite directions, it's negative. So for the applied force, the block slides down, the applied force is up, so it's negative. For part B, same thing. The motion is parallel direction. I have a force. If the force is not already parallel, then I have to do sines and cosines. So I'll break it up just like I broke up my triangles before. One side is parallel, one side is perpendicular. And when I say parallel and perpendicular, I mean parallel to the floor and perpendicular to the floor, the ramp's floor. And so I take the parallel component of the gravity, the weight, take that number times the distance traveled, and then positive or negative again. Here, the block slides down, gravity pulls me down, they're the same direction, so he's positive. All right, another example. Slightly different style of question, but basically the same thing. Let's say what you have, let's say we have a table. Here's a table. believe it or not. And I have a box. The box has a mass of 20 kilograms. Let's say the table is 4 meters off the ground. You are going to take this box and lift it up at constant velocity and place it on top of the table. So if you lift the box at constant velocity, and place it on the table, how much work is done by you and how much work is done by gravity. Okay, so that's a nice question. Slightly different than the ones before. Here, we're not sliding along the ground or anything like that. We're lifting an object that has a certain weight. We lift it in a particular way because obviously, let's say you're lifting weights. Well, the first way you can lift it is you lift it nice and slow. Pick it up as slow as you can. You're not forcing it up as hard as you could possibly force it. You're just picking it up normally. The other way you could do it, of course, is to pick it up really quickly, almost like you're going to throw the weights up into the air. Well, obviously, the second way takes more force to lift. It's harder for you to lift it that fast than it would be to just barely lift it off the ground. So we have to be able to figure out how much force does it take for me to lift this box. Because obviously, if I want to find the work, it's force times distance. So I need to know what's the force. So the very first step is going to be to try to figure out what force is required to lift this box to the table. So for that, we use F equals ma. And we look at the box. So the box has the weight pulling him down and your applied force trying to pick him up. Right? Those are the two forces that act on this box. The weight trying to hold him down to the ground, and you lift. Whatever your force of lifting is, I call it applied force. With some force, you lift. So, what are all the forces on the box? Minus mg down, plus your applied force up. That equals ma. Well, what's the acceleration for this problem? Because, of course, it's m times a. Well, look at the problem. It says if you lift the box at constant velocity. Well, constant velocity means there's no acceleration. That's the definition. So constant velocity means acceleration is 0. So now we have an equation. I want to solve this for the applied force. How hard do I have to lift? Applied force is equal to mg. 20 times 9.8, which is 196. I now know how hard I have to pick it up. Of course, if I try to pick it up very quickly, maybe I picked it up with an acceleration. In that case, ma would not be m times 0, it'd be m times whatever a is. And then this force would be a bigger number, because it'd be mg plus ma, whatever ma is. But in this particular example, ma happens to be 0, so the force I need to lift is just equal to its weight. Now I can solve the problem. Part A, how much work is done by you? That is, the force you apply. Well, work is force applied times distance. All right, which direction does the block move, or the box move? Well, it moves up into the air to try to get on top of this table. So it moves in the y direction. So that means I only care about the y component of my applied force. Well, thankfully, the applied force is already in the y direction. So that's good. What's the applied force? 196. How far does the block go? From the floor up to the table is 4 meters, so times 4. And then we ask the question, is this positive or is it negative? Well, let's see. The box is going to go from the floor to the table, so it moves up. Which direction is the applied force? Lifting up. Since they're both up, it's positive. So the work done by my applied force, 784 joules. All right, what about part B? The work done by gravity. Well, that's the force due to gravity times distance. All right, so what's the direction of motion? Y direction. So for my force due to gravity, I only want the y component. Well, gravity's already in the y direction, so perfect. I just plug it in. What's the weight? What's the force due to gravity? mg, and mg is 196. How far does the block move? From the floor up to the table is 4 meters. And then is this positive or negative? Well, the box moves up to the top. Gravity, however, pulls down to the bottom. So since they're in opposite directions, this work has to be negative. Thus, the work done by gravity is negative 784 joules. So there we go. Answered the question. Now look at the answers we have and notice that what this means is if you lift an object and you just barely lift it, you're not lifting it extremely quickly or anything. If you just lift it to move it up, the total work done on the object is 0. That's interesting to note, and it'll come back in a little bit, actually our next lecture, when we discuss how work and kinetic energy are involved. But for now, just note, if you lift an object with constant velocity, the total work done is 0, because gravity balances you out. If you lift harder, then there's some excess work, because your applied force is bigger than weight. And of course, if you don't lift hard enough, then weight wins, and the box is going to fall down to the ground. Now, obviously, how can this be modified? Well, we can always take this, lift the box at constant velocity, and switch it with an acceleration of 3 meters per second squared. Then what would I do? All I would do is I'd take this A and I'd plug it in right there. So this would be m times 3, 20 times 3, which is 60. So then this would be plus 60. This would be plus 60, which would be 256. So then part A, instead of 196, would be 256 there. And so this will be a bigger number. Now, would it affect part B? No, it would not affect part B, because part B just asks about the weight. And the weight is what it is. It doesn't care if it was accelerating or not. So part B would stay the same, but part A would be a bigger number. Which means there's some net work done to this box. It's not a total work of 0, it's a total work of whatever it happens to be. Okay, so I hope that's clear. Because, you know, you could have any story. Here you're lifting a box to the table. It could be a helicopter is lifting a crate, and a helicopter accelerates with a certain acceleration. Well, that's just what I did here in red. It's the same problem. It's just a different story, different words. But at the end of the day, you should be able to do something like this. Given some system with a bunch of forces, whatever they are, can you calculate the work done by each and every force? Some are going to be zero because those forces might be perpendicular. Some you have to find components. Like here, the F1 was at an angle, so we had to do a component. Or here in example 2, gravity was a y force, but I'm looking for a parallel direction. So again, I had to do components. And then sometimes you don't have to do components. If the force is already in the right direction, then you just stick the force in the way it is. But note, they're all being done in a very similar way. Don't let the story of the question bother you. That, oh, I haven't read a question that sounded like this. At the end of the day, if what you're looking for work, you ask yourself, number one, in which direction will the box or the object move? Whatever direction you say, that's the component of the force you have to use. So if you say it moves in the x direction, then work is done with x component forces. If things are at angles, you get the x component. If things are in the y direction, those forces give you zero work. If you say the direction of motion is in the perpendicular direction, then only perpendicular components give you work. Parallel stuff would give you zero. Okay? What you're going to find, at least I found over the semesters I've been teaching, is this set of material, work and energy upcoming, tend to be a little easier than kinematics and Newton's laws. And you can see the equation, F times X, that's an easy equation to do. The only way that can get complicated is when you have to do the components. But if you've been keeping up, then you've had a lot of practice finding components. If you need more practice, then you better practice, because components come up all the time. And that's the only place, in my opinion, you can mess up these problems. Everything else is straightforward. But if you don't know when to use sine or cosine, well, that could get you into trouble. Also, when is a work positive and when is a work negative? Again, it's not, oh, the force is to the left, so the work is negative. That's not how it works. It's all about if the force and the distance are pointing in the same direction, then it's positive. Whether it's left or right doesn't matter, as long as it's the same. And if they point in opposite directions, then it's negative. So if it's left, one is pointing to the left, the other is pointing to the right, that's negative. If one is pointing down and one is pointing up, that's negative. If they're both pointing down, that's positive. If they're both pointing up, that's positive. So easy rule, it's just don't let the rule of to the right positive, to the left negative make you think this is how you do it here. It's not that. It's same direction versus opposite direction. All right, so those are the examples for work. I hope this helps with the practice problems and such. And you can see there's not much to it. There's only so many variety of questions I could ask you about work. The next topic we'll do is called the work energy theorem. And as I said, that's going to tell you about how applying work to an object will change what's called the kinetic energy. And kinetic energy is basically a measure of its motion, how fast something moves. And so the reason I showed you this example here, and I talked about what's in red if we're moving something with an acceleration, is because that's going to pop up with this kinetic energy business. If I lift something harder than I have to, so if I apply a force bigger than the weight of the object, it's going to make the object accelerate. It's going to get faster and faster. So you're going to apply a very high speed, or at least a change in the speed of the object. But if I just barely lift it, so I lift it with constant velocity, the velocity doesn't change. Whatever it is, that's what it is. And it doesn't get faster, it doesn't get slower. That's what we're going to talk about next time, and you'll see that, again, it's going to be a small equation, but it'll be easy to work with. So practice these problems, make sure you're keeping up, and I'll see you next time.